And
Okay na po, sir.
okay na.
Thank you po.
Okay, thank you. Right. The point of ANOVA is to determine whether the difference of the mean values of two or more groups are actually bigger than the internal variance within each group or each data set, right? You're just trying to see if the variance within each group is like it is actually smaller than the difference or the difference between with the other means compared to the other means. Like you can see that the you're trying to see if the difference is actually big enough to justify or to conclude that this group is different from another group, right? And the example we have here is, for example, the blood plasma of patients, right? Like the control group here, a healthy patient will have a blood plasma NETs. I'm not sure what that means, but it's around 0 to 50. And if you compare it, for example, with a patient a, with, with a group of patients having viruses, their blood plasma tends to shoot up, right? So if you're gonna try to look at the center of the data points, like the approximate locations of their means, you can see that their means are actually you can see a big jump, right? You can see a big difference between their means. Okay. But you also want to see if this big difference is actually significant compared to their internal variance, right? And that's what we simply do in ANOVA, right? And normally when your ANOVA is used when your response variable or the data that you're obtaining is numerical. For example, weight, for example, length, or other numerical values. And we usually try to use ANOVA as a starting test whether there is a numerical difference between two groups, right? Now, what we're doing for this exercise is just a one-way ANOVA, right? One-way ANOVA means you're just dealing with a single factor. For example, you're dealing with crop yield, right? So that's your response variable. For example, you're measuring the weight of crop yield per plant, and you want to see what is the effect of fertilizers or other effects of different of let's say changing the fertilizers, right? And when you have more than two groups, you can use ANOVA to see if there's a difference between these at least three groups of data sets. Since there's only one factor being changed, like the absence or presence of fertilizer, we can describe this problem as a one-way ANOVA. On the other hand, if you apply two factors, the problem becomes a lot more complex because, for example, if you change the fields or like you change the soil type and you also change the fertilizer, you're now dealing with one, the type of the fertilizer, two, the type of the soil, and three, the interactions between the fertilizers and the soils. Right? So you're actually introducing like three factors, although you nominally only added just one factor here, right? right? And that's the difference between one-way and two-way ANOVA. But for now, we're just gonna deal with one-way ANOVA, right? And now we will need our studio for this exercise, right? The example problem is the effect of a chemical treatment on the weights of plants, like your vegetable plants. And we will be using a built-in R dataset to conduct a one-way ANOVA test. So our data now will come from within the R Studio. Our and our studio has a database of different practice data sets, which you can try and try when you're trying to learn R. Right. First step is to formulate the null hypothesis. Right. Null hypothesis, or H naught, means that the mean of the original plant is just the same as the second first group and the second group of plants. This means that the three groups of plants are essentially the same in terms of their weight, or in terms of their average or mean weights. Okay? Meaning the treatment isn't actually working, right? That's our null hypothesis. Null hypothesis always tends to default towards the conclusion of no difference, or no new information. The alternative hypothesis is that not all the means are equal. It means that the weights of these plants are actually different, and there might be some, or these might be attributable to the effect of the treatment. Right? And now we can, of course, before like any other statistical method, the first step is to actually visualize the data. I mean, it's always this is the standard practice. You always have to visualize your data before you actually apply any sophisticated analysis, just to ensure that your results later on are actually reasonable and they actually make sense. Okay. For this exercise, we actually need to install packages. Particularly for now, we need the DP layer package, right? So I hope you can copy paste this code from the PDF file, right? So the command, it's install the dot packages, and then just include the DP layer in your command. I'm gonna run this, right? And there's a warning. I need our tools. So I actually need to install our tools first, and I'll try to see or figure out how do I do it. right? Sorry for the dead air, right? Our first problem now is how do we install our tools for our program. Apparently, we need it in able to use DP layer, right? And I found the R tools installer here. But before that, we need to determine first the version of our R program, right? And upon checking Stack Overflow, you simply have to type r.version in order to determine the version of your R, right? And I think the version of my R is 4.4. And from there, it means that I need to download RTools 4.4. And then send the link in the chat box. Or you can just search for RTools, right? And you will immediately see the result in your search engine. Anyway, we let's just download this RTools and install it. um huh, right? And you can just click the RTools 44 installer and wait for that to download. Right? While we're waiting for that download, I'll just skip over to the setting up of the data variable part. In this part, we just need to declare a variable named my data and then just call out the plant growth name. This name is a reserved name for the plant growth dataset in R, right? So let me try calling that dataset. So it's a built-in data, right? When I call the plant growth name, the R terminal immediate or console immediately showed me a data set containing like a weight and a group, a column. Right? This is our built-in data, and we're gonna because we don't want to mess with this built-in data, we will just store it or just declare a new variables and we can basically duplicate this built-in data. So my underscore data and then plant growth, right? Then again, you can check if you have properly stored the data in your variable by calling your my data variable, right? And it's showing up properly. And now let's go back to our RTools installer. I hope this works. I think I'll need to restart my R Studio, so I'm gonna save this session for now. Right, I'll just give you an overview of the steps while waiting for the installer. The next step is to check your data, all right? And actually, I think this step is not really necessary because you can easily check the plant growth data by just calling the variable. And you can see you saw earlier that the data only contains like 30 entries. But anyway, as part of the tutorial, the first step in checking your data is you are like going to initialize your random numbers. This set seed command, the purpose of this command is to simply ensure that your random numbers in your test or in your calculations are consistent. Like, yeah, it's quite counterintuitive, but you're essentially setting or trying to get a set of random numbers based on the number you have inputted. But anyway, this is just a trivial command. So you need this set of random numbers when you're calling this dp layer sample underscore n command. So what does this command do? dp layer is a set of packages, and this double colon simply means that you're calling a command within the dp layer package. And your command here is sample underscore n. And sample underscore n, what it does is that it tries to randomly pick out a few data points within your data set, right? And the format here is your first input is the name or the name of the variable containing the data set. And then the second input is the number of data that which you want to sample. This command is useful. For example, if your data set like consists of around 1,000 or maybe even a few hundreds of data points, right? And you don't really want to look at the data set while the data set is arranged in a numerical fashion because you will have a bias, right? So you want to see, for example, a sample number of data points, okay, on a random on like by doing some random sampling, right? Right, we're done installing our tools. Let's try to start our studio and install again the DP layer package. So first, let me check if my variable is still working. So it's good. It's still alive. Let's go back to the installation of the DP layer package. Right, it worked, I think. So we can see here, package DP layer successfully unpacked and the five sums checked. The download the binary packages are under the downloaded packages folder. Right, so far so good. Now we can proceed with checking of our data. So again, it's not really necessary because our data set is only like 30 data points. Although this command can be useful if your data set again is like 100 or 1,000 data points worth, right? And you can see that this command allowed you to see like 10 random data points from within your data set. All right. So you can see the ranges of the weights are like around 3.83 to 6.15. And then we have here another term in R, the levels. Levels are just the unique values, all right, on a given column. So for example, you're looking at the column group and you have different entries here. You have your CTRL or your control. TRT1 means treatment 1. TRT2 means treatment 2. And you can see here that these names are actually repeating. Like control, treatment 1, and treatment 2 are repeating names. And these are what we call levels, right? These are the unique values that are present in your data column, right? And in here, our command is levels, right? So the levels will just show you the unique values for that given list of data or for that given column of your data. And inside the levels command is the name of your variable and then $ group. This means that you're trying to access or you're trying to input the group column from your data set, right? And the output is that you can see the three different unique values, your control, your treatment 1, and treatment 2. Okay. So again, this is useful if your data is actually like a large data set. Okay. For now, it's hard to appreciate this function because you can clearly see the three levels or the three unique values within your data set. Okay. Again, we have another command here. This command, the function of the purpose of this of this ordered command is to determine if your data set is actually ordered alphabetically. Okay. So this ordered function, so you can see here, yeah, you can see two parts within this command, right? First is this my data $group, and then you have this pass function, right? This arrow is a pass function. And then the second part is this ordered function. You can see the ordered and then parenthesis, or like as I've said before, any word followed by a parenthesis is just a function or a command in R, right? Ordered, and then the first input here or the first parameter here is the my data group, sorry. And then the next input is levels is equal to C, and then within the C is your control 1, treatment 2. So again, let me break down this one. Um, C is a combine command, right? C parenthesis simply means combine. And treatment 1, treatment 2 are simply what we call the strings. Strings are to simplify, these are like words. Okay. In R, you have to again to enclose words in parentheses, otherwise it will treat this text as a variable name, right? So you're specifying a list or a sequence of text or strings, control, treatment 1, treatment 2, and you're trying to combine them into a list, right? That's what C does. And then levels is simply like this is simply specifies how you want to order your data set, right? So what this does is that ordered simply determines if your data set is actually ordered, correct? If it's ordered, it won't do anything. If it's not ordered, then it will try to use the levels parameter to determine how you want to order your data set, right? Since our data sets is already ordered, this command will actually do nothing. But anyway, let's try using this. Okay. And then again, try to call again your my data. Okay. So again, the first data still is 4.17. The last data is still 5.26. The middle data is still 5.87, right? So in here we can see that the command actually did nothing. But again, this command is going to be useful if your data set is like a huge mess of list of numbers and you like simply want to organize them. Okay. But of course, as students, if this is too confusing for you, I mean, I understand if this is too confusing. You can always do it in Excel and then just import it again into R. Anyway, now the next step is to calculate these summary statistics of your data sets. All right. So what we're gonna do here is first is we're gonna group the data rows by the group column. All right. So each data set here, so each data point here, right? As long as they have the same control, they have the same group name, like all the data points which have the control, which have the group name as control, all the data points whose group name is control will be put under one list or one variable, if you want to imagine it like that. All data sets with group name of treatment one will also be grouped together, and all of data sets with treatment with the name of treatment two will be grouped together. Okay. So again, what we're doing here, we're gonna call the DP layer module, so we can call their functions. So let me check what DP layer does for your benefit. Wait a minute. All right, sorry for the unexpected break. Right, you can see here the different functions within the DP layer package. You can see you can filter your data sets, you can summarize multiple values down to a single summary, you can arrange your data sets, right? So so it does a lot of stuff which I don't really know yet. Anyway, at least I know now that the summarize function, I think this is a UK or yeah, UK Australian English. You can see here that the summarize function is actually coming from your DP layer library. So let me break down again what's happening here. You have this group by command, and you are trying to segment or split your data into groups. And your first input is your data variable. So this is your data set. And the second parameter or the second input is the group. So group by most data operations are done on groups defined by variables. Group by takes an existing table and converts it into a group table where the operations are performed by group. All right, so at least that makes sense. The group by works by inputting the name of your input variable, and then the simplest way to use it is to again input the next input would be the name of the column within this variable, right? So what we're doing here in the group by is we are inputting this my data variable, and then we're telling the group by function to use this column name as a basis for the grouping, right? And what it will do is it will simply look for, again, it will look for names with the same value, and they will group them together. And then after that, we have this pipe function. So I think this is like the opposite of the pass function. The pipe function, what it does is it instead of putting a value towards a variable, you are actually doing something in reverse. You're actually taking this result, whatever is the group, whatever is the result created or the output created by the group by function, right? And the result will be groups of data sets. So you're expecting like three groups of data sets. What the pipe function does is that it essentially throws out or pipes down the output into the function below, right? And this is the next part of our command. You have your summarize command, right? And you have like three parameters here. First parameter here is the count. You have your count parameter, and count equals to n open parenthesis. This simply specifies the summarize to simply count the number of data points per input, right? And we have here like three inputs, right? So your control, treatment one, and treatment two. You also have your mean, right? And the mean here. So essentially here, what you're doing here is you're actually defining variables, sorry. So your first variable is your count. So your count variable will store the result of the n parenthesis, which simply counts the number of your data sets. The next thing here is your mean. The mean variable will take in the results of the means. And the mean function here, the first input here is the column containing the weight. Okay? And then the second parameter is the specification of the mean calculation. So na.rm simply means that you will simply remove all the invalid or no data values when you're calculating the mean of your data group. And then the SD variable here will simply store the result of your SD function. And again, the input to the SD function is the weight column. And again, you're trying to remove all the invalid or no data values by specifying na.rm equals true, right? And if we input this one, so you can actually just copy the whole command with the comments included, right? The R Studio will simply ignore all those comments in your command. Nah, it's not working. Uh, okay, that's weird. Anyway, since the data isn't cooperating, let's just delete the column, the comments for now. Oh, I see the problem now. I missed a step. I was supposed to initialize the DP layer library first. So let me hit that. No DP layer. Okay. Okay. Attaching package DP layer. Following objects are max. Warning message. Package DP layer was built under R4.4. So I don't care. Let's just try the command. Anyway. try this again. Okay, so for some reason the console was able to recognize my command after I activated the DP layer library, right? So this is my result. You have a table of 3 by 4, and the group here shows you your different control. So the group column shows you the name of the data group. So you have your control, treatment one, treatment two. The count shows their count. So you have 10 data sets per group. The mean is also shown, right? You can see 5.03, 4.66, 5.3, and then the SD's standard deviation. All right. So you have here like the summary statistics of each group from your data set. Now, the next step is to visualize our data. So just install ggpubber package. Right, it's working, thankfully. After we're done installing your ggpubber package, our next step is to again activate our library. Otherwise, the console won't be able to recognize your command. Just copy that, and you're getting warning messages, but they actually are telling you that the ggpopper packages were actually activated, so that's good. Now, again, you have this ggboxplot function or command. Sorry. And the first parameter here is the variable that you're gonna use. And then you define the X as the group, right? So the X-axis here shows the different groups. So it will treat the group column again. It will treat the group column as the X-axis. So it will automatically separate your data again by the name of the group, or by the name of the group on this column. And then the Y-axis is the weight. So this is your Y-axis, and it will simply take in the data from the weight column. Okay. And then the color scheme will be based on the group. So if you have 3 groups here, you will be getting 3 color schemes. And then again, you can also specify the palette of colors to be used. So I think these are the specific colors for green, yellow, and orange. And then you can also specify the order, right? And also specify the labels. Okay. So again, let's copy this command. And you're actually seeing an interactive interpretation of the command. You're seeing the colors immediately. And after entering the command, I can see a box plot. So again, what do these box plot means? Right. So again, just a review of your box plots. Box plots show you your minimum. So this is your minimum value. It also shows your first quartile. So again, before I think it's better to introduce first your median. So this is your median or your second quartile. Again, your median is your middle value. If you're gonna arrange your value like one by one, and if you're gonna arrange all the values in your data sets one by one, and you're just gonna pick the midpoint of that line of values, that would be your median. All right. Now, if you're gonna pick the median of your median, the lower, so if this part will be further subdivided into its median, so again, just pick the middle point of this line. That would be the first quartile, right? So that's the median of the lower half of your value. This is your lower quartile. And then again, if you're gonna pick the median of your upper half of your data, that would be the third quartile, right? So minimum, sorry, minimum um 1Q, second quartile or your median, third quartile or your, yeah, that's your third quartile. And then this is your maximum, all right? From here, you can see the general clustering of your data, how the data is distributed. For example, for the control group, you can see that the median and the third quartile are actually close together, right? Right, there's some clustering between the median and the third quartile. By clustering, I mean that there's a dense occurrence. There, you have a lot of data sets occurring between the median and the third quartile, right? Because this part like represents the this part represents so each segment here represents like one fourth of your data, right? So this part is one fourth of your data set. I mean, if you're gonna count it in terms of number of data points, so this is a one fourth of your data set. This is another one fourth of your data set. This is another one fourth, and this is another one fourth, right? So you can see that in a short distance of values, you actually have this concentration of your one fourth of your values, right? And then after that, you have more or less a scattered a scattering of your data. Like again, this is a one. This spans a huge range of weight values, but this is just constituting the one fourth of your data. All right, so I hope I was able to refresh you on how to read box plots. Right. The second one is your treatment group one. So I think there's something weird here. I'm not sure why I'm getting dots here. Of course, I can't really remember that. So Yeah, so the dots are actually outliers. Okay. Meaning outliers are like defined as the gaps in your data. Okay. You can see here, if this is your distribution and somehow the data is like interrupted, like you get some gaps here, you'll be getting some dots in your box plot, right? Again, if you're gonna look at this treatment one group, the yellow one, you can see here that the first quartile, so this is one, two, three, like the third quartile, the median, and the first quartile are actually evenly spaced. So you have here a more or less a normal distribution because most of your data set are like concentrated around the median. You have here, this is your mean value, and the upper tail or the max value. So this is your upper tail, and then you have a data gap here and here. Hence, you have some dots in here, right? Okay, so again, these are like outliers. Okay, there could be a phenomenon explaining that, or there could be probably a problem with your sampling or whatsoever. Okay, so there are many things that could explain your outlier. Either way, it's a weird number. Okay, statistically speaking. You also have here your treatment group two. You have your median and your first quartiles being close. So you can see here again, in a short span or a short range of values, you have a concentration of the 1/4 of your value. So you can see that you can call this a clustering of your data set in this area. Okay. So again, overall, the lengths of your box plots are more or less similar. Like if you're gonna measure this one, this is like maybe 4 minus 6. Oh, sorry. Like 2 units of length. Okay. 5 to 3, 7 to 5. So more or less they have a similar lengths, similar variances, right? And these it means that this data is qualified for ANOVA because they have more or less similar magnitudes of variances. Okay. You also have your mean plots. Again, this is just very similar to how we did the box plot. Okay, so I'm just gonna copy the command. So SE here means standard error. Okay, you also have your standard deviation. Okay, let's just try this one. Right? So you can see here the medians being connected. Okay. So I think this these lines are represent the standard error. And again, more or less, they are more or less slightly similar in terms of lengths. And again, that means that they're qualified for an ANOVA analysis because standard error is usually used as a proxy for variance. Now let's do the ANOVA test, right? The the command here is rest.aov, right? So this is your analysis of variance. Sorry, this is your variable name. Okay, dot rest.aov is your variable name. And then AOV parenthesis is your analysis of variance command. And then the syntax here is that the first parameter here is the column containing the values that you want to analyze. And then you have this, I forgot the name of this character. After this one, you state the name of the column containing the group names, and then comma, you put in your you declare the variable being analyzed, okay, or you specify the data being analyzed. So in this case, the data being analyzed is your my data, right? So I'm just gonna enter this one, and then it doesn't show anything. Okay, so this is actually a long result. So we're gonna summarize rest.aov, or you can also call out the rest.aov if you're curious. Rest.aov. Okay, so don't really understand the result, but it's easier to interpret the summary rest.aov. So I'm gonna call that again. All right. Let's quickly interpret or discuss the results. So here you have your group and then your residuals. Right, the first column is your degrees of freedom, right? So this is simply calculated as the number of data points or categories minus one or minus another value. I'm gonna show that later on. Sum of squares, again, this is just your mean, your data point value minus your mean, and then you square it. That's your sum of squares. Mean square or the variance or the spread, you simply take the sum of squares and then divide it by the degrees of freedom. So 3.766 divided by 2 is 1.8. And then 10 divided by 27 is 0.3886. And then you have here the F value. This is I think this is an important number here. This tells you the ratio of variances. This tells you the variation between the sample means divided by the variation within the samples, right? So in simple terms, it shows you the ratio. Okay. You're comparing here like the variation or the differences between the means versus the internal variation within each sample. Okay. The bigger the variation between the sample means it simply indicates that there is a intrinsic difference between the samples, meaning they are actually different, right? Therefore, the higher the F value in ANOVA, the higher the variation between the sample means relative to the variation within the samples, right? So as long as you have a high F value, it simply means that you have different data sets. The higher variation between sample means relative to the variation in the samples, the higher the chance that the difference between the samples is not due to sampling errors, rather it is due to inherent differences. Right? Like again, in short, they are legitimately different if the F value is high. And the higher the F value, the lower the corresponding P value. So the P value again is like a measure of our level of confidence. The lower the P value, the higher our confidence. The bigger the P value, the lower our confidence. So I'm gonna discuss again the PR parenthesis F. That's the P value. So again, if this value, or we call this the P value, if the P value is lower than our chosen level of significance, we can reject the null hypothesis. So again, the null hypothesis is a hypothesis of no difference. So we're gonna reject that now and conclude the alternative hypothesis, stating that at least one of the samples are actually different. For example, if we want to choose a 95% confidence level, right? We need a significance level of 0.05. So that simply is 1 minus 95%, that's 0.05. If the p-value is smaller than our significance level, we can reject the null hypothesis and accept the or conclude and accept the temporarily accept the alternative hypothesis. Okay. So in this case, if we're gonna use the typically used 95% confidence level, our significance level is 0.05. If 0.05 is bigger than your p-value, so in this case 0.0159, so the p-value here is actually smaller than 0.05. Therefore, we can reject the null hypothesis and conclude that the at least one of the samples in our data are actually different. Okay, right? So that's how analysis of variance works. We have another example problem here pertaining to carbonates. So happily enough, this is closer to geology. So suppose we obtain 5 pieces of calcite cemented sandstone. So this is actually 9 pieces, sorry. Each of the 5 rocks in our collection is lithologically different, but so you have a coarse grain sandstone, you have your clayey sandstone, you have your ferruginous or iron-rich sandstone, and so on and so forth. But you want to know if they have the same carbonate content for some reason, right? So let's park now why you want to know that carbonate content. But for now, you just want to know, do they have the same carbonate content? So I regret that click. All right, let me just read the brief of the example problem. So how do we determine if they have the same level or same amount of carbonates? One of the typical practices is to simply take one piece of rock, and then if this is you and this is a rock, you take a geologic hammer and you smash the rock into pieces. Okay? And now what you get is a mess. Sorry. You, you now have what you call replicates. No, once you smash the rock into pieces, you get many replicates, right? So each fragment or each replicate, you determine the carbonate content by submerging them under a acidic solution, right? So the acid solution will dissolve all the carbonates, and what will remain is the non-carbonate material, right? So after you weigh all the remaining materials, you can deduct or you can deduce or infer. Sorry, I can't really. You can calculate the actual carbonate amount of carbonates dissolved, and therefore you can calculate the carbonate content of each fragment or each replicate. All right. Now, the purpose of making or generating replicates is to determine if there is a variability within the weight, within the actual procedure of measuring or determining the carbonate content. Okay. So you're simply creating fragments so that you can actually repeat the carbonate content determination process. Okay, so that you can actually generate a statistical data set for each per rock sample or rock type. Now, if the variation within the replicates or within the fragments are large compared to the differences between the specimens, like meaning within a replicate, within a set of replicates, you get a large variation compared to the variation within the means of the rocks, and then that simply means that there is something wrong with your carbonate determination methodology. Okay, like for example, maybe your acid is not strong enough to dissolve all the acids, or maybe after dissolving all the carbonates, some of the residual matter are actually spilling out, or you're like losing some stuff after doing the carbonate content determination. Or maybe the replicates are like not really evenly distributed in terms of their composition whatsoever. Anyway, that's not part of our problem for now. Our problem for now is simply determine if the carbonate contents of these rocks are different or not. And this is the table of our data. This is taken from the book of Davis and Samson, I think. Although you can also download the dataset from the Kansas Geological Survey website. I think for just a trivia, Kansas Geological Survey is probably one of the coolest geological surveys I've seen. This is a Kansas Geological Survey is like a state geological survey in the US. So it's like the equivalent of maybe the Mines and Geosciences Bureau. But at the same time, they operate closely with a university. Okay, so their research and actual geological survey functions are like always like synchronized, and they were able to actually develop a lot of applied geological methods. Okay, So one of them is, of course, your stats in geology. You also have geophysical methods, seismic geophysical methods developed in Kansas Geological Survey. Anyway, end of the trivia. So you have here your data showing the samples, your sample 1, sample 2, sample 3, 4, 5. And these are the replicates. The parentheses or brackets only indicate the order of the analysis. So you can just ignore this. Okay, for now, these are not really important, right? Now, our first job here is to import the data. So again, you need to import or read a delimited file. So you can use the read CSV function or you can use the read delim function. So what I'm gonna do here is I'm gonna look for my data set. So one va.text or one va.csv. So let's try the one va.text. Again, the secret here is to hold your control key while right clicking your file so that you can copy the path of your file. And then maybe just put it on a notepad temporarily. And then just copy here this is the name of my variable, carbonate rocks, pass. So I need to enclose my path on a parenthesis. I also need to double the backslashes. So read dot delim parenthesis, double the backslashes, and pray that the command will actually work. Okay. Right, so I called the command and I can see here like 5 samples. So your carbonate content, your calcium carbonate 3, your carbonate, sorry, calcium carbonate content, and then your sample name. So sample 1, 2, 3, 4, 5, 6. So they are arranged in order. That's good. It's gonna reduce the number of stuff you need to do. I don't know why this command is in here. I'm just gonna delete it for now, or I'm just gonna cross it out. So I think you also need to, I think you need to import the data. So I'll just go back to that later on. Okay. So I've already discussed the F. Okay. So these are the values being calculated. So you can also load the CSV file. So this is the alternative to the read.delim. You can use this command. Okay. So we don't need to sort out the dataset because it's already sorted automatically. So you don't need to use the ordered function. So now we can just jump into the summary statistics. So again, you need to activate your DP layer library. And then again, we use the group by command and then input. We use the group by command so that we can split your data into different file virtual files or inputs. So we just input the name of the variable containing the data and then we input the name of the column that will be used to sort out our data set. So this command will split your data into 5 different data sets and then they will be passed into this string of functions, the summarize function. So I'm just gonna copy this command and pray that it works. Okay. So I'm seeing here your sample column. So you have different sample names, 1, 2, 3. The count shows you how many samples, how many replicates or fragments you have per sample. So 6 each, totaling to 30. Your mean and standard deviations, right? So these are correct values. Okay. So I know these are the correct values because these are the results shown in the Davis and Sampson textbook, right? So if you want to practice data sets in R, practice data sets that involve geology, you can just refer to the data sets in your Sampson and Davis book, right? Now, the next step is to do a box plot graph using this command. Okay, so there's something wrong with the command. I actually need to activate the ggpubber first and then copy the ggboxplot command. Okay, so there's something wrong. Error, unexpected invalid token and sample Y calcium carbonate and color. So you can see here that the parenthesis here is actually weird. And this is one of the problems when you're typing your command in PowerPoint or Word and then you paste it in R. So you can see here that this quotation mark symbol is actually different from this quotation mark symbol. So our workaround here is to simply retype the parenthesis, right? And now the console is now recognizing the colors, meaning I think I fixed something. So let's try it again. And now we get a box plot of our samples. So again, supposedly their variances, the lengths or the spread of their data is more or less the same in terms of their length. So this data set is eligible for ANOVA. At the same time, if you're gonna look at the means of your data sets, you can immediately see some jumps in their mean values. So you can expect that there will be at least one one sample which would have a different mean compared to the rest, right? So that's our expectation. Okay. One mean value would be different from the rest. Right? You can also do your mean plots. Okay. So again, we're just looking here at the error bars. The standard error bars again more or less have the same lengths, and standard error can be used as a proxy for variance. And since they have similar lengths, we can conclude that this data set again is eligible for ANOVA. And then we do the analysis of variance command. Now in here, we actually have your F value is actually quite small. Okay. So if we're gonna use a bago. I think there's something wrong. I think there's something wrong here. I mean, uh, not sure why I'm getting that result. I think there's something wrong with the dataset. I think it's better to use the .csv file. Um, so let's redo the solution, especially in the import part. I'm just gonna change the path name here. Okay, and Okay, sorry, I need to do some double backslash. Okay. So let's try repeating the check the data set. So we have 19 as our first data, 19.1 as our last data, 8.7 at number 15, all right? So we can skip this. We were able to do this step properly. So we can also skip this one and just go straight to your analysis of variance. Okay. So I'm able to reproduce the earlier results. So I think something happened with the um, import command. I think one of the problems I did is I didn't specify the header and the class of numbers, right? This defining the classes of your date of your values is important. I think you're familiar with the integers, double floats, floats, strings. You might have encountered them in your maybe some of your programming classes. And these are important, especially in R when the commands are actually relying on the format of your values in order to process the command correctly. Okay. So we just summarize the results. And you can see here your F value is again it's big, it's larger than one. So you can consider this a large F value. So this simply means that the variances between the means are quite big compared to the internal variances within each sample. The p-value is 5 raised to the negative 5 times 10 raised to the negative 5. So it's a very, very small value. And if you're gonna compare it to a significance level of 0.05, you can definitely say that this one is a much, much smaller value, meaning we are really confident that there is a at least one different data set within this group. All right. So our exercise or your exercise or your assignment is to work with zeolites. Okay. And you're gonna use the Hewland underscore mod dot CSV to analyze 93 data points of Hewlandites, right? And these are the deliverables for this exercise, right? Hypothesis statement, box plot, mean plot, AUV, AUV summary, and then what is your verdict? Are you gonna reject or accept the null hypothesis at 0.05 significance level? And then you also get some penalty when your code is incorrect or it doesn't match the results that you're getting. You also have a research problem. Okay, so yeah, just read the problem. All right, so do you have questions regarding the tutorial or you have clarifications? Okay, so I think you maybe you don't have questions, it's already late. So if you have questions later on, you can still post a message in Blackboard or to my email. All right, thank you for joining this tutorial session, and I'm gonna have a good evening. I'm gonna end this online class. Okay, okay.
Thank you po, sir.
Thank you.
Thank you po.